day we were talking about how do you figure out the likelihood of some event happening or not happening. Okay? And one scenario that is fairly straightforward to do is something like flipping a coin, heads or tails. What's the probability of heads? 0.5. What's the probability of tails? 0.5. Now, let me rephrase the question. What percent of the time do you get heads? 50%. What percent of the time do you get tails? 50%. Remember, probabilities are always between what two numbers? 0 and 1. And percents are, in this case, between 0 and 100. So be careful. If you're asked for a probability, that number should not be bigger than 1. Neither can it be negative. Okay. We talked about if a family has 2 kids, okay, got 2 kids, what's the probability that there are 0 boys, that there's 1 boy, that there are 2 boys, or that there's 0 girls, 1 girl, or 2 girls? And we talked about that you can list the different ways to get a family with 2 kids. I grew up in a family with 4 kids. There are more combinations there. We'll take a look at that in a little bit. But one way to figure out a probability of a particular event happening is to list all of the outcomes and count up how many of those outcomes are the one that you're hoping for. Okay? And put that out of however many outcomes there are total. For example, let's say that you have 2 dice. And to keep this relatively simple, let's say the one dice only has 2 sides, numbered 1 and 2. So when you, that sounds more like a coin, doesn't it? Okay, but trying to keep this example small, you can get a 1 or a 2. The other one has, let's say, 4 sides. So you could get a 1, 2, 3, or 4. The outcomes that you could get by using these two are 2, 3, 3, 4, 4, 5, 5, 6. When we list the outcomes like this, there are how many different results that we could get? Well, it looks like there are 8 of them. You see it? Now you may say, but 5's up there twice. You're right. There are 2 different ways to get a 5. Okay? One of them is by rolling a 2 and a 3. The other is by rolling a 1 and a 4. Those are different, aren't they? Okay? You can ask things like, what is the probability of x equals, oh, let's say 6. X just means the outcome you're interested in. What's the probability that we get to move 6 spaces? Well, that would be 1 out of 8. Where you in the numerator put down the number of ways that what you're interested in can happen. In the denominator put down all the different things that can happen. Does that make sense? You can also ask things like, what's the probability that it's less than or equal to, oh, let's say 4. Well, we know there are 8 outcomes total. Now, how many different plays give a result of 4 or less? Now, so let's count them. 1, 2, 3, 4, 5. If you were playing a game and you get a roll that's 5 or bigger and you wind up in, I don't know, the miry pit. Okay, and if you roll 4 or less, you stop just short of it. Are you more likely to wind up in the miry pit, or are you more likely to wind up on solid ground? 4 or less is going to put you on solid ground, 5 or more, and you wind up in the quicksand. got two choices, right? What's the probability of being on good ground? It's 5 out of the 8 different ways that you can move. So that's more than half, isn't it? So you've got a better probability of being on the solid ground than you do of landing in the quicksand. Does that make sense? Do we actually know what's going to happen to you when you roll the dice? That's why you roll them. See what's going to happen. Okay? This that we have right here is what is termed theoretical outcomes. Okay? The theoretical outcomes. In theory, these are the things that should happen. In theory, this is the number of times these things should happen. Does that make sense? Now, there's a difference between theoretical outcomes and real life. When you jumped in your car this morning to come here, theoretically, you should end up where? Here. Yeah. However, okay, could something happen that would result in you ending up other than here? Yeah, you all know that. So every time you jump in your car and you decide I'm driving to UCBA, you're doing an experiment. Am I really going to get there, or who knows? I may wind up in a traffic jam and detour and get lost and wind up out in Loveland somewhere. That's really lost, isn't it? Okay? It could happen. Hey Siri, get me home. I'm done for the day. Okay? Theoretical is listing everything. Everything's good, clean, perfect, da-da-da. Experiment is you see what happens. We're going to talk about that in a little bit here with some coin tosses. So, there are different outcomes possible. One's theoretical. That's the nice, clean, everything works the way it's supposed to. There is experimental. What an experimental would look like is you take these two dice and you throw them a bunch of times. You throw them 50 times. And you write down the outcome that you got each of those times. Okay? Or we team you up in twos and we ask you to start flipping coins. One person flips the coin, the other person writes down the results. Head, tail, 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 head, head, tail, tail, head, 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 tail. And you keep going. And we just do it for 5 minutes. And let's say that after this 5 minutes of doing this experiment, heads, I'm just making these up, okay? Let's say that the heads wind up being 637 times, and the tails wind up being 583 times. Now, this is for everybody in the class. We added up everybody's total heads, everybody's total tails. Boom, there we go. If we're doing this experiment, we could, from this, compute what does it appear the probability of flipping a head is. Well, to get the probability of heads, we're going to list the number of times that heads came up over, what number goes in the bottom? All the flips together, right? Well, to get all the flips together, we're going to add these. And this is going to be a 2, and this is going to be a 12. So it's going to be 637 out of 1,220. From that, you can compute a probability. I'm going to take the 637 divided by the 1,220 equals, we wind up with 0.522. According to our experiment, you should get heads 52% of the time. Theoretically, is that true? No. You should get heads what? 50%. But would you be upset with this outcome? No. Why not? It's close. Now, here comes the fun part. Well, we're going to take a look at it a little bit later. How close is close enough? How close do you have to be to the theoretical outcome and be comfortable, yeah, nobody was cheating? How far away do you have to get before you start to be suspicious? You know, I don't trust that Chuck. He's wearing a long sleeve shirt today. I think he's got something up his sleeves other than his arms. Okay? And that gets kind of interesting, trying to figure out how close is close enough. We'll talk some more about that. There's a third way to get probabilities. The first way is a theoretical outcome. The second way is do an experiment. The third way is subjective. What does the word subjective mean in general? Yeah. Okay, it's just your preference. Really? You think that's a nice color on that car? Obviously in there is the thought that I'm thinking that thing is ugly. But is the looks of that car something that we could determine theoretically? Or is that just something subjective? It's subjective. Folks have different preferences, don't they? Okay. When you're asked, what's the probability of da-da-da, hey, how likely are you to be able to get to the dinner tonight before 6? Because if you get there early, I need some help getting things set up. Okay? Tomorrow, the guys, Daniel's team's coming over for lunch at our place. They'll be there at 12:30 with empty stomachs. 12, 16 to 18-year-old guys, empty stomachs. This sounds dangerous. Okay? And I happen to ask one of the dads, how likely is it that you can get there to help set things up ahead of time? Well, pretty good chance of it. That's subjective, isn't it? He's thinking about what he expects to have happen this evening, what he expects to have happen tomorrow morning, and when he expects the car to start, and he expects there to not be any traffic jams, and he expects to not hit any deer on the way to our place. And based on all these things that he's guessing, yeah, I think I can do that. Pretty good chance I'll be there, Chuck. That's purely subjective, isn't it? Does he have any actual data about what's going to happen? No, he knows what's happened in the past. Okay? Does that make sense what subjective is about? You're just kind of asked to take a guess at it. Okay? Very different from theoretical or even experimental. Okay, we talked about this a little bit the other day. We want to make sure, because people miss this every test, and it drives me nuts. And I intentionally was making some noise to try and draw your attention to it. Probabilities have to be between what two numbers? 0 and 1. Yes, way to go. And if I ask what's the probability of something, and you put down 0.37, that's great. If you put down 37, what's that mean you're thinking? A percentage. You're not asking a probability, you're asking a percentage. Hey, would you go out in the garage and get the basketball? And you come back with a football. Okay, well, it's a ball. Okay, I guess we can throw it, but that little puppy's going to be hard to bounce in the driveway and shoot. Okay? Be careful. They are different. I get it. They're related to one another, but they're not the same thing. Keep them separate. Okay? Okay, notice here. Theoretical method for computing outcomes. Count the number of ways that you can get the outcome. Figure out how many ways, how many outcomes you can get. Okay, so you count up how many outcomes you can get. So like when we were rolling the 2 dice in the earlier example, there were 8 different outcomes. Okay, then count up how many ways can you get the event you're interested in. And you take whatever it is you're interested in, over the total number of different outcomes. Wow, that's a surprise for you, isn't it? No new news there. You've been doing that since a long time ago. Okay? We've talked about these for theoretical outcomes. We've talked about this as well. 52 cards. Real fair question might be something like, you got a standard deck of playing cards. What is the probability of randomly, out of a fanned deck, choosing Jack 3 times in a row? Pulling a Jack out 3 times in a row. What's the probability of pulling out 3 Jacks in a row? Is that very good, or yeah? If you fan a deck and I pull out 3 Jacks in a row, are you suspicious that something's up? Yeah. Now, I would be suspicious too. Why? It's not very likely to happen. Now, here comes the question. What is the likelihood, the probability of pulling 3 Jacks in a row? Well, the probability of 3 Jacks equals, what's the probability of pulling one out of a fan deck on your first draw? 4 out of 52. Now, when you pull 1 Jack out, does the rest of the deck remember what you did and then say, okay, we got to make sure that Taylor pulls out a not Jack this time? Does the deck remember that? No. So each of these draws is independent. What you do the next time, or what you pull the next time, has nothing to do with what happened the last time. But the probability of a Jack on the second draw will have changed. Why? Taylor's standing there with a Jack in her hand. How many are still in the deck? 3 out of 51. And lo and behold, she pulls out a second Jack. Whoa. Okay, she's good. Now, she's holding 2 Jacks in her hand. How many are still in the deck? How many Jacks are still in the deck? Need to be a little more careful on what I say. 2 Jacks. How many cards total? 50. What is the probability of this actually happening? Well, all I got to do is to do parentheses. 4 times 3 times 2. Close the parentheses. Divided by parentheses 52 times 51 times 50. Close the parentheses. Whoa. This is going to be 0.0018. As a probability, that's pretty small. That's pretty close to 0, isn't it? As a percent, what percent of the time? You slide the decimal over 2 places. And what we're going to have is 0.18%. This means that if we were to fan the deck 1,000 times and let Taylor pull 3 cards, it would happen basically 1 time out of every 1,000. Not very likely to happen, is it? Now, one of the things that we're also going to do, I'm not going to ask for a show of hands here. I don't know how many of you might play various lottery tickets and stuff like that. My father-in-law calls it a voluntary tax on the stupid. His words, not mine. Why? But if I hit the lottery, do you know what they'll do to me? Here's an interesting one. They've done studies of people who've won the lottery. 2/3 of the people who win the lottery are where in 5 years? Bankrupt. That's right. They win $15 million and 5 years later they're bankrupt. How do you do that? Suddenly you've got all these new friends you never knew about. And they've all got their hand out. people, the worst thing that ever happened to them is to win the lottery, because they wind up in worse shape financially 5 years down the road than what they were before they bought that ticket. Whoa. Okay, we'll do that probability, not today, but later. All right. When you are doing a listing of all the outcomes, you need to be careful to do it in an organized fashion if there's much going on. Now, if it's flip a coin twice, that's pretty easy. You already know tail, 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 head, head, tail, head, head. I mean, that one you can pretty well work out without a whole lot of difficulty. However, in my family, growing up, there were 4 of us kids. Poor mom and dad, they were outnumbered. Okay? There were 4 kids in the family. Fortunately, I was the oldest. Better than being the youngest. You don't get beat on as much. Okay? You get blamed for more, but you don't get beat on as much. In our family, the oldest and the youngest were the boys. In the middle 2 were the girls. What is the probability of a family of 4 kids going boy, girl, girl, boy? Is it very likely or not very likely? Well, if you check on here, how many outcomes are there total? They've already listed all the outcomes for you. Let's see. 1, 4, 6, 4, 1. Get rid of that for right now. It's insistent. It's going to have that up there regardless. 16 different outcomes. How many of those outcomes go boy, girl, girl, boy? 1. So if you have a bunch of families at a picnic or whatever, and they all have 4 kids in them, there's only 1 out of 16 that's going to go boy, girl, girl, boy. I apologize to my younger brother many times as adults. Okay. Oldest, youngest. Okay. Does this make sense? You could also change it up. Not worry about the birth order, but just ask, what is the probability of getting 2 girls and 2 boys? Which is what our family has. Now, a lot of people right away leap to 50% because it's half girls, half boys. Is it really a 50-50 chance that you're going to wind up with 2 girls and 2 boys in the family? Well, we know it's going to have 16 different possibilities. And how many of those are 2 girls and 2 boys? 6. It's actually 3/8 or 0.375. A little bit less than half, isn't it? Okay. Does that make sense? A very important move to be able to make when you're working with probabilities is being able to create a table with all the possible outcomes. On something like this table, where you're listing lots of different events, you've got to take it in an organized fashion. So, for example, if you were asked to list all the possibilities of a family with 4 children, you don't just, well, let's see, boy, girl, girl, boy, 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 girl, girl. You want to take it in a more organized approach than that, something more structured, so that you're sure to get all the possibilities. So, for example, you could start with one extreme, girl, 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 girl. 4 girls. Then go to 3 girls. Well, that means we got to throw a boy in here somewhere. Heaven forbid he's the youngest. Put him up here. And all I'm going to do is I'm going to slide the boy over in the birth order each time. And there's some structure to that, isn't there? Then you can come back, okay, now it's time for 2 girls. And I'm going to slide this boy over one place, which means the girl's going to go there. Now I'm going to slide that boy over one place. Then I could start sliding the second boy over. Does that make sense? And then check and see, are there any other options? Okay. And then drop to one girl and then no girls. Okay, so when you're making these lists, running them like that's a good idea. And then you just use the usual routine. Now, here's something kind of intriguing. Let's say you do an experiment, flipping coins. All you're interested in is the number of heads when you flip 2 coins. So, I'm going to take 2 coins and go, blink, catch them, tail, head. Okay, all I'm interested in is the number of heads, 1 head. Flip them, blink, whoa, head, head. I would record a 2. Okay, well, let's say Jack and I were doing this, and he was flipping the coins, and I would just write down 0, 1, 2 each time, counting up the number of heads that Jack flipped. Okay, and we do this 100 times. Okay, so we've got the results from flipping 2 coins, 100 separate events. Would you be suspicious if there were 0 heads 22 times? That would mean 22 times Jack flipped 2 tails. Does that sound suspicious or not? So you're saying, yeah, I got to keep an eye on him. Maybe let's switch it. You were writing them down and I'm flipping them, so I'm the suspicious one. How's that sound? Okay, don't want you winding up in trouble. 0 heads 22 times. Well, let's think about that for a minute. The outcomes are tail, 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 head, head, tail, head, head. What is the probability of no heads? It's 1 out of 4, isn't it? Which is 0.25. Or what percent of the time will you get no heads? 25% of the time. On 100 flips, how many of them would be no heads, theoretically? 25. So is 22 all that weird? Oh, maybe not. Maybe that's close. Is it perfect? No, but you don't expect it to be an experiment. Now, 1 head. There are 2 different outcomes here that have 1 head. So the probability of 1 head would be 2 out of the 4 different options, which would be 0.5 or 50%. Would that be kind of weird if the team of Jack and Chuck flipped 1 head 51 times? Would you be suspicious that they were doing something weird there? Okay. The probability is 50%, right? So out of 100, you should get how many? 50. We got 51. Is that pretty good? Yeah. Okay. Not suspicious of too much there. Probability of 2 heads. Well, that's going to be 1 out of 4, which is 0.25. 0.25 would mean 25 times we should get 2 heads. Came up with 27. Is that pretty close? Yeah, that's not bad. Okay. Let me ask you this. If we came up with 0 heads 3 times, would you be suspicious of that? That's off pretty far, isn't it? Does that mean that we cheated, or is it possible to flip no heads? I mean, could it happen? It could. Is it likely to have happened? No. So it's either one of those really unusual things like Taylor drawing 3 jacks, okay, or there's something up. And it's up to you to decide which it is. Does that make sense to everybody? actually I want to point out quick like that the last class had questions on is one, run through the null and the alternative hypothesis again. How do these things work? Okay. And the other thing is, how do you compute that margin of error stuff?